Welcome back. Last episode, we spun a 2D region around an axis to get a 3D solid and computed its volume. Today, we ask two more questions about the same curve y equals f of x. First, how long is the curve itself? Not the area beneath it, not the volume it sweeps. The actual length of the curve as a one-dimensional object, the number you'd read off a ruler if you could uncoil it. Second, when we rotate the curve around an axis, it sweeps out a 2D surface, a sphere, a trumpet bell, a torus, whatever. What's the area of that surface? The skin of the solid, not the volume. Both formulas share one factor, the square root of 1 plus f prime of x squared dx. That's the length of an infinitesimal piece of the curve, the slant hypotenuse of a tiny triangle with legs dx and dy. Pythagorean theorem on an infinitesimal triangle, integrated. Two formulas, one geometric idea. Let's build it. Start with the central idea, the infinitesimal triangle. Take any smooth curve y equals f of x and zoom in on a tiny piece. As you zoom, the piece looks straighter and straighter. In the limit, it is straight. It's a tiny line segment. Call its length ds. Now look at the triangle. The piece goes from a point x, y to a nearby point x plus dx, y plus dy. Horizontal leg dx, vertical leg dy, slant hypotenuse ds. Pythagorean theorem, ds squared equals dx squared plus dy squared. Take the square root and factor out dx. ds equals the square root of 1 plus the quantity dy over dx squared times dx. Since dx equals f prime of x, we have ds equals the square root of 1 plus f prime of x squared times dx. That's it. That's the whole new ingredient. Every formula today is built by integrating something against this ds. The arc length is just the integral of ds alone. Sum up the lengths of all the tiny pieces. The surface area will be the integral of 2 pi f of x times ds st circumference times slant width, summed up around the curve. One picture, one factor, two formulas. Let's keep going. Here's the picture, made concrete. A smooth curve y equals f of x in blue. Pick a tiny segment of it in the dashed gray circle. Zoomed up on the right, that segment is a small right triangle. Horizontal leg dx, vertical leg dx, vertical leg ds. Pythagoras, ds equals the square root of dx squared plus dy squared. Now imagine doing this everywhere along the curve. Chop the curve into 1,000 such tiny triangles. Add up all the slant hypotenuses. You get an approximation to the total length of the curve. Take the limit as the chops get finer and you get the exact length. L equals the integral from a to b of ds, which is the integral of the square root of 1 plus f prime squared dx. The Riemann template again. Chop, approximate by something straight, sum, take limit. The only new content is what each small piece is and how we measure its length. Here, a small piece is a tiny line segment, and we measure it by Pythagoras. Formal statement of the arc length formula. Take a curve y equals f of x, smooth on the interval from a to b, where smooth means f prime exists and is continuous. The arc length L of the curve from x equals a to x equals b is the limit, as you chop more and more finely, of the sum of the lengths of the straight line approximations. That limit, by the argument we just made, equals the integral from a to b of the square root of 1 plus f prime of x squared dx. The derivation is one line. Partition the interval from a to b into n pieces. On the ith piece, the straight segment approximation has length the square root of delta x sub I squared plus delta y sub I squared, which factors as the square root of 1 plus the quantity delta y sub I over delta x sub I squared times delta x sub I. By the mean value theorem, delta y sub I over delta x sub I equals f prime of x sub I star for some x sub I star in the ith piece. So the sum is the sum of the square root of 1 plus f prime of x sub I star squared times delta x sub I, a Riemann sum for our integral. Take the limit. That's the formula. It looks more complicated than the area or volume formulas because of the square root, but conceptually it's the same recipe. The integrand is the geometric measure of an infinitesimal piece integrated over the interval. First worked example. Arc length of y equals x to the 3/2 from x equals 0 to x equals 4. Step 1. Compute the derivative. F prime of x equals 3/2 times x to the 1/2. Square it. F prime of x squared equals 9/4 times x. Add 1 plus 9/4 x. Take the square root of 1 plus 9x over 4. That's our integrand. Plug into the formula. L equals the integral from 0 to 4 of the square root of 1 plus 9x over 4 dx. This is a substitution problem. Let u equal 1 plus 9x over 4. Then du equals 9/4 dx, so dx equals 4/9 du. When x equals 0, u equals 1. When x equals 4, u equals 1 plus 9, which is 10. Rewrite the integral in u. L equals 4/9 times the integral from 1 to 10 of the square root of u du. The antiderivative of the square root of u is 2/3 u to the 3/2. So L equals 4/9 times 2/3 times u to the 3/2 evaluated from 1 to 10, which equals 8/27 times the quantity 10 to the 3/2 minus 1. Since 10 to the 3/2 equals 10 times the square root of 10, we get L equals 8/27 times the quantity 10 root 10 minus 1. Numerically, 10 root 10 is about 31.62, so L is about 8/27 times 30.62, which is about 9.07. So the arc length of y equals x to the 3/2 from 0 to 4 is about 9.07. Sanity check, the straight line distance from 0, 0 to 4, 8 is the square root of 16 plus 64, which is the square root of 80, about 8.94. The curved path is slightly longer than the straight one, as it must be, and only by a little. The curve doesn't bend much. The numbers pass the Snell test. Notice why this example was carefully chosen. The derivative f prime of x equals 3/2 times the square root of x squares to 9/4 x, a polynomial. So 1 plus f prime of x squared is a polynomial, and its square root is integrable by a simple u substitution. For most curves, 1 plus f prime of x squared is a mess, and the integral has no elementary form. Arc length integrals are notoriously ugly. We picked a clean one. Quick aside, because students always wonder, the arc length integral, the integral from a to b of the square root of 1 plus f prime of x squared dx, looks innocent, but for most functions f, it does not have a closed form antiderivative. The square root of 1 plus a square is almost always intractable. Even something as simple as the arc length of a parabola, y equals x squared, requires you to compute the integral of the square root of 1 plus 4x squared dx. That's doable. You use a trig substitution, 2x equals the tangent of theta, and you end up with logarithms. But it's not pretty. Worse, the arc length of y equals sine x is the integral of the square root of 1 plus cosine squared x dx. This is an elliptic integral. There is provably no antiderivative in terms of elementary functions. Historically, elliptic integrals were how mathematicians first realized that some perfectly reasonable integrands just don't have nice antiderivatives, and that observation eventually gave us the entire theory of elliptic functions. So the punchline is, arc length is conceptually easy, the integral of ds, but computationally hard. The integrals that come up in textbooks are carefully chosen, like our y equals x to the 3/2. In real applications, you usually evaluate arc length numerically. Conceptually clean, in closed form, a luxury. Now the second formula, surface area of revolution, setup. We have a curve y equals f of x with f greater than or equal to 0 on the interval from a to b, rotated around the x-axis. The curve, being 1D, sweeps out a 2D surface, a cone, a sphere, a trumpet bell, depending on the curve. We want the area of that surface. Slicing argument. Pick a tiny piece of the curve at position x. As we just saw, this piece has slant length ds equals the square root of 1 plus f prime of x squared times dx. When we rotate this tiny piece around the x-axis, what does it sweep? It sweeps a thin band, a narrow ribbon wrapping around the axis. The radius of the band is f of x, so its circumference is 2 pi f of x. The width of the band, measured along the slant direction of the curve, is ds. Approximating the band by a flat strip, its area is circumference times slant width, 2 pi f of x times ds. Substitute in ds and integrate. S equals the integral from a to b of 2 pi f of x times the square root of 1 plus f prime of x squared dx. That's the surface area formula. Critical detail, the width of the band is ds, not dx. If you mistakenly write 2 pi f of x dx instead of 2 pi f of x ds, you've computed the area of a flat horizontal strip, not a slanted band. The slant matters, sometimes enormously. If the curve is steep, ds is much larger than dx. The square root of 1 plus f prime squared factor is the slant correction. One subtle point, because this is exactly where everyone trips. Why slant width ds and not horizontal width dx? Because the local geometry of the surface is a cone frustum, not a cylinder. A cylinder has vertical sides, a cone frustum has slanted sides. Our surface locally is slanted. Quick refresher on the cone frustum. A frustum is a cone with the tip cut off, leaving two circular ends of radii r1 and r2, and a slanted lateral surface of slant height l. The lateral area of this frustum is pi times the quantity r1 plus r2 times l, when r1 and r2 are nearly equal, which they are for a thin piece. This is approximately 2pr times l, with r the average radius. Match terms to our setup, r equals f of x, the radius at position x, and l equals ds, the slant width. The length of the curved segment from x to x plus dx, not the horizontal distance dx. So the lateral area is 2 pi f of x times ds, which is exactly what we wrote. If instead you use the cylinder formula 2 pi rh with h equal to dx, you get 2 pi f of x times dx. That undercounts whenever the curve is slanted, which is almost always. For a very steep curve, the undercount is huge. The square root of 1 plus f prime squared factor is the correction from horizontal width to slant width. Don't drop it. Here's the picture. The curve y equals f of x in solid blue above the axis, with its mirror y equals minus f of x in dashed blue below. That mirror is what the curve sweeps to when rotated. I've drawn one representative band at position x, between two thin ellipses that are the cross-sectional circles of the surface. The band shaded in red, very gently flaring outward because the curve is sloping upward. Its radius at the front face is f of x, labeled vertically. Its slant width ds is labeled along the diagonal ribbon between the two ellipses. The area of this band, approximately, is circumference times slant width, equals 2 pi f of x times ds. Integrate over x from a to b, summing all the bands, and you get the total surface area, s equals the integral from a to b of 2 pi f of x, times the square root of 1 plus f prime of x squared dx. One picture, full formula. Bands of slant width ds summed around the curve. Second worked example, and one of the most satisfying calculations in calculus. Rederive the surface area of a sphere. A sphere of radius r is the surface of revolution of the upper half circle y equals the square root of r squared minus x squared on the interval from minus r to r rotated about the x-axis. Compute the derivative. By the chain rule, f prime of x equals minus x over the square root of r squared minus x squared. Square it, f prime of x squared equals x squared over the quantity r squared minus x squared. Add 1 plus x squared over r squared minus x squared equals r squared minus x squared plus x squared, all over r squared minus x squared, which equals r squared over r squared minus x squared. Now the magic. Compute f of x times the square root of 1 plus f prime of x squared. That's the square root of r squared minus x squared, times the square root of r squared over r squared minus x squared, which equals the square root of r squared minus x squared times r over the square root of r squared minus x squared, which simplifies to just r. The integrand collapses to a constant. The radius of the curve and the slant factor cancel perfectly, leaving r. So the surface integral is s equals the integral from minus r to r of 2 pi r dx equals 2 pi r times 2r equals 4 pi r squared. 4 pi r squared, the classical surface area of a sphere, derived in 3 lines. Archimedes proved this in the 3rd century BC, using a much harder slicing argument. He famously asked for a sphere inscribed in a cylinder to be carved on his tombstone because he thought the relation between the two, the sphere's surface area equals the lateral surface area of its bounding cylinder, was his most beautiful theorem. We just got the same result by writing down one integral and letting the algebra simplify. Notice the geometric content of the simplification. The radius of the band at position x is small near the poles, where the absolute value of x is close to r, and large near the equator. But the slant factor goes the other way. The curve is steep near the poles, large slant, shallow near the equator, slant near 1. The two effects exactly cancel. A perfect geometric balance. That's why the integrand is constant. Quick historical and geometric aside, because the cancellation we just saw is one of the most beautiful facts in classical geometry. Archimedes proved the following theorem, sometimes called the hat-box theorem. Take a sphere of radius, r inscribed in a cylinder of the same radius, r and height 2r. Think of the sphere sitting snug inside the cylinder. Now slice both with two parallel planes perpendicular to the cylinder's axis. You get a strip of the sphere, a spherical zone, and a strip of the cylinder. Archimedes proved that the lateral surface area of the spherical zone equals the lateral surface area of the cylindrical strip, always, regardless of where the planes are. The narrow strips near the equator have a lot of circumference but small slant, and the strips near the poles have small circumference but large slant, and these two effects exactly cancel. That is exactly the cancellation we just saw in the integral. The integrand 2 pi f of x times the square root of 1 plus f prime of x squared collapsed to the constant 2 pi r, which is the circumference of the cylinder at any height. So the sphere's surface area equals the cylinder's lateral surface area, 2 pi r times 2r equals 4 pi r squared. Archimedes was so proud of this result that he asked for the sphere and cylinder figure to be carved on his tombstone. 2 centuries after his death, Cicero is said to have found that grave and identified it by the figure. We have rederived this 2,200-year-old theorem in 3 lines of calculus. That's the power of having the right tools. Brief history of how this formula came to be. Pre-calculus, Archimedes already knew specific surface areas, the spheres, the cones, the paraboloids. He proved them by the method of exhaustion, a kind of pre-calculus limiting argument that gives you specific answers for specific shapes, but no general formula. He had no integral symbol. Newton and Leibniz, in the 1670s and 80s, wrote down the general arc-length formula, the integral of the square root of 1 plus the quantity dy over dx squared dx on largely heuristic grounds, the infinitesimal triangle argument we used. They were spectacularly successful at computing arc lengths of specific curves, cycloids, parabolas, the semi-cubical parabola y equals x to the 3/2, the one in our first example, and many others. But they couldn't fully justify why the sum of chord-length approximations converged to a well-defined limit. The rigor problem: when you chop the interval into n pieces and approximate the curve by a polygonal chain, why does the total length of the chain converge to a definite number as n approaches infinity? For wiggly curves it might not. There are fractals like the Koch snowflake whose chord approximations diverge to infinity. The honest condition turns out to be that f' is continuous, which on a closed interval gives uniform continuity, which guarantees the Riemann sums converge. Cauchy in the 1820s finally made this rigorous with the modern epsilon delta machinery and the theorem that continuous functions on compact intervals are uniformly continuous. So the arc-length formula was guessed by Newton, used by everyone, and proved by Cauchy, a 150-year gap between intuition and rigor. Calculus has many such gaps. The formulas work, the proofs that they work are harder than they look. Zoom out. We now have 5 integral formulas, all built from a single curve y equals f of x on an interval from a to b. Area under the curve, the integrand is f of x, the height of a thin vertical strip. Area between two curves, the integrand is the difference f of x minus g of x, the height of a vertical strip in the bounded region. Volume by disks, the integrand, the cross-sectional area pi times f of x squared, the area of a thin disk. Arc length, the integrand is the slant length of a tiny segment, the square root of 1 plus f prime of x squared. Surface area of revolution, the integrand is the area of a thin band, 2 pi f of x times the square root of 1 plus f prime of x squared. 5 formulas, 1 template. In every case, the integrand is the geometric measure of an infinitesimal piece, and the integral sums those pieces. Area, length, volume, surface area. 4 different geometric quantities, all built from the same Riemann recipe. The only new ingredient in this episode was the arc-length element ds equals the square root of 1 plus f prime squared times dx, born from Pythagoras on the infinitesimal triangle. Once you have ds, the surface area formula is just the integral of 2 pi f of x times dsc, circumference times slant width, integrated. That's the unifying lesson of this whole arc of the series, from episode 9 on. Different geometric questions, same integration template, different infinitesimal pieces. 5 pitfalls, since this material gets tangled easily. 1. Don't drop the 1. The arc-length integrand is the square root of 1 plus f prime squared, not the square root of f prime squared, which is the absolute value of f prime, which is what you'd get from a horizontal derivative alone. Not 1 plus f prime, which is what you'd get from a careless algebra step. The 1 comes from the dx squared in Pythagoras, and dropping it is the most common error. 2. It's the derivative squared, not the function squared. Students sometimes write the square root of 1 plus f of x squared from muscle memory of the volume formula. No, it's f prime. Surface area has both f and f prime, 2 pi f of x times the square root of 1 plus f prime of x squared. Don't confuse the roles. 3. Expect square roots and ugly integrals. Most arc-length problems require U substitution or trig substitution. Some have no closed form. If you find yourself looking at a clean polynomial antiderivative, you got lucky. Usually the square root forces work. 4. The surface area band has slant width ds, not horizontal width dx. The Frustum formula uses slant. If you forget the square root of 1 plus f prime squared in the surface area integral, you're treating each band as a cylinder, not a cone, and you'll undercount badly whenever the curve is steep. 5. Axis matters. Rotating about the x-axis gives circumference 2 pi f of x. Rotating about the y-axis gives circumference 2 pi x. Sketch first, identify the radius of each band, then write the formula. Universal preventative, sketch the curve, sketch one representative piece, label its dimensions. Same advice as last episode. Geometry first, then algebra. Recap. The infinitesimal triangle. Zoom into a tiny piece of a curve. It looks like a right triangle with legs dx and dy and slant hypotenuse ds. Pythagorean theorem gives ds equals the square root of 1 plus the quantity dy over dx squared times dx, which equals the square root of 1 plus f prime of x squared times dx. That's the new ingredient powering this entire episode. Arc length. Sum the slant lengths of all the tiny pieces. L equals the integral from a to b of the square root of 1 plus f prime of x squared dx. Worked example, y equals x to the 3/2 on the interval from 0 to 4 gave L equals 8/27 times the quantity 10 root 10 minus 1, about 9.07. Surface area of revolution about the x-axis. At each x, a tiny piece of the curve sweeps a band of circumference, 2 pi f of x and slant width ds. Multiply, integrate. S equals the integral from a to b of 2 pi f of x times the square root of 1 plus f prime of x squared dx. Worked example, the sphere of radius r. The integrand collapses to the constant r by perfect cancellation of radius against slant. The integral gives s equals 4 pi r squared, Archimedes' classical result in 3 lines. Key conceptual point. The infinitesimal pieces of a surface of revolution are cone for sta, not cylinders. Use slant width ds, not horizontal width dx. And the meta lesson, same Riemann recipe as every episode since the second one. Write down the measure of an infinitesimal piece. Integrate. The content of the integrand is the geometry of the piece. Next episode we pivot. We've spent 10 episodes on continuous integration. Next we shift to discrete sums, sequences, and series. The sum of a sub n instead of the integral of f of x dx. Same summation spirit, very different convergence questions. See you there. That's arc length and surface area. If this helped, hit like, drop a comment, and consider subscribing. It's the single most useful thing for the channel. Post your favorite arc length problem below, especially the ones where the integrand simplifies miraculously, like the sphere did. Those are the hidden gems. Next episode, sequences and series. We leave the continuous integral behind and meet the discrete sum, the sum of a sub n instead of the integral of f. New convergence questions, new tests, new tools. Same mathematical spirit. See you there. Arc length and surface area complete the geometric application cycle. From a single curve y equals f of x, we now extract 4 quantities: the area beneath it, episode 2, the area between it and another curve, episode 9, the volume it sweeps when rotated, episode 10, and now the length of the curve and the surface area it sweeps. 4 geometric measures, 1 Riemann template, write down the infinitesimal piece, integrate. The new ingredient today is the square root of 1 plus f prime squared x, the length of a tiny segment of the curve, born from the Pythagorean theorem on a triangle with legs dx and I. That single factor drives both formulas. Next episode, we pivot hard. We leave the realm of continuous integration and walk into the world of discrete sums, sequences, and series. The Riemann template stays, but the indices become integers, and the questions become, does this infinite sum converge, and to what? Subscribe so you don't miss it. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.